You can keep talking. I'm just going to start playing a little bit. How's it looking? Can you guys figure out it was dy? Because it's around a vertical axis of revolution if you are just memorizing the forever card. Or because all of our circular discs, if we were to actually show this shape, which would be like a cone with its top cut off. You guys see it? You don't have to see it necessarily, but it'd be like a cone. With its top cut off. You see it? Like a little volcano in that shape. Technically it'd be more like that, sorry. When that shape rotated around. But even if you can't draw the picture, you don't necessarily have to. What you need to realize is every time we're doing one of these solids of revolution, it's always going to have a circular disc because you're revolving. Right? The one that we're expressing, once again, would have like little ridges on it, but that's okay once we throw it in an integral and make the depth, which this time is a height, is a vertical depth, which you can look just by looking at the rotation arrow and giving it depth. If you're a visual person, that's the way to realize if it's a vertical depth, everything needs to be in terms of y, or whether it's a horizontal depth, everything in terms of x. So I went after my pi r squared. Whoa, 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 why did I pick disk and not washer? There's no hollow. Or you can think this region and the axis it's revolving around is, what was that word I was using yesterday? Oh, you guys just don't know that word, do you? Flush. If it's flush against, it's completely meeting all the way against. I think that's also I don't know if I would say woodworking term, but like if you were making some sort of bookshelf, you would have like vertical pieces and horizontal pieces, or do you guys still make the like the candy machines or the boxes? You want your pieces to match up perfectly, or if you're doing any sort of interlocking pieces, you want them to match up perfectly, flush against, not having like weird warping or some edges meeting and some edges not. You want it flush against. Anyway, there's no space. There's no hollow. There are no places where this area deviates from that axis of revolution. Anyway, so it's a disk, so all I needed was pi r squared, but r in terms of y, so I went ahead and figured out that r was right minus left because everything's in terms of y, which our forever card has back here, right guys? I mean, our washer one does too, but the washer one we have to be aware or be thinking of a lot more stuff because we have to think of big r's and little r's, but still right minus lefts are what's being used. But the disk one is where we really got that idea across in the sense of we are going to be able, as long as the region is flush against the horizontal axis or flush against the vertical axis, I can just use my top bottom or my right minus left as far as my radius, right? But coming back to our example, too far, lo siento. There we go. Coming back to our example, it was flush against. It was a disk. It was a vertical axis of revolution, or our cross sections have vertical depth. Either way, everything in terms of y. Then what was my left though? That was the one other place you might have gotten tricked. If right is the line written in terms of y, what's the left? Yeah, you guys saw that, right? X equals and x equals. Minus 0 doesn't really make a difference, so no big deal. Some of you are like, why do you keep on minusing 0? It never makes a difference. These are not the only axes of revolution they're going to use. What if they used y equaled -3 and it was minus -3 instead? Does that make a difference? Yeah. Or what if I was choosing y equals 2? Now this region wouldn't be revolved around y equals 2 because some would be above, some would be below. That would be a mess. But let's say y equals 5. There we go. It could be rotated around y equals 5. Then once again, the subtraction, which we're not going to talk about top-bottom, would be really nasty with this example if we were revolving around a horizontal axis. But either way, I know, the minus 0 right now isn't making a difference, but seeing the right minus the left and being able to plug the left in this spot always is really important. Sorry, then you guys were plugging in your calculator. I just need to know how your brains work. Question, what are you guys doing? Are you doing the integral right away and then remembering the 1/4 pi? Or are you putting the 1/4 pi times the integral? Or are you doing pi? I just need to know. Some of you didn't pull out the 1/4. That's fine. What did you do with the pi? Did you write it inside the integral, outside the integral? Did you save it till later, or did you put it in right away? Outside and right away or later? Okay. Anyone who said later, danger. What's the danger? Forgetting it. Or getting a decimal and being like, oh, it's right there. I got one. You just got it wrong. Yeah? Okay. Because didn't we see yesterday in that one multiple choicey one? It was a disk one? What were we doing? Oh no, cross sections. They had the without pi and they had the with pi. You gotta be careful. Their answers, unlike our pre-cal multiple choice test from last year, their answers are like, oh, common student mistake number 1, common student mistake number 2, common student mistake number 3. That's why some of you guys in your test, you're like, oh, I felt good. I actually circled things. And then you're like, oh, I did the common mistakes. Which is okay, because that means you have an idea, unless you're just guessing and happening to get half credit without even knowing what you're doing. But anyway, those of you guys that plugged it in, let's see if our decimals matched. What did you end up getting? 6 point what, Patricia? Nice. I heard it all over. Does that sound good? That's what you would think. So those of you guys that got that in your calculator, how did you put the integral in? Did you put it just with x and say forget it, or did you use the alpha y? The x worked, but AJ, guess what? If you had used alpha y or a or b or c or d or e or f or g, because you can actually put like the letters in, all of it would be the same answer. So the nice thing is, because it's oriented in terms of y, your calculator doesn't really know in terms of x, in terms of y. It's just like, I don't know, it's a variable. So as long as you have the correct numbers for the y's, the expression for the y's, everything in terms of y, when you go to plug it in your calculator, you can use whatever variable you want. You're okay. Does that make sense? The only time that gets dangerous is if we were graphing this, and it was written in terms of y, and then we go finding intersections or zeros, and our calculator's saying, well, you told me the y was an x, so... and it's doing like stuff in the graph. That gets tricky. Because in your mind, you're thinking in terms of y, but in the calculator, it's thinking in terms of x, so your points might get switched, but otherwise, you're okay. That also has to go with, or that also applies to if you have functions in terms of t, you can use x also in your calculator, but we don't see t's as much as BC does. Kiddos, let's go ahead and, I know I gave you a handout, and we're going to look at that handout in a second. There's a cool illustration that I still don't have the program to show you, which is kind of sad. I do have at the end of notes, it's been saved for the last few days, I do have the old school ones as far as Patrick's and Khan Academies, but I had you go find these tutors and the Dr. Marchese in the Google Classroom announcement with cross sections. So I assumed that you guys should be able to look pretty quickly around. And if you guys noticed, Colin had a part 1 and a part 2. He has like a whole series of lessons with practice problems. Patrick has ones for not just washers, but also discs. He has ones with vertical lines, horizontal lines. But I put a quick note about the cylindrical shells, not cylindrical shells, even though I was the one that put that link on there first and had to change it, so I apologize for that. But Dr. Marchese also has ones. But I told you yesterday it'd be a great idea. Don't worry about that. That's practice test stuff that we haven't gotten yet. I told you guys yesterday that whichever tutor you chose, you should keep watching their videos, right, to get some more exposure and some more practice problems, etc., because these get trickier. And this is going to be a place where it gets trickier. So get this out and get this ready. But first, let's peek at our homework. Some of you guys have started, some of you haven't. And let's see if there's anything in particular we need to watch out for as far as you guys finishing up homework tonight so we can go over questions tomorrow. So I'm opening up homework. Those of you that have started it, you might want to open up your homework spirals. I might go over a couple specific questions if you have them ready. If you don't have them ready, that's okay. Let's just make sure that we know what each of the sections are specifically saying, okay? So in the first 6, actually it looks like the first 10, they give us actual, let me get rid of that guy. They gave us actual pictures of regions that are being, do you guys see it? Okay, so is homework starting off with cross sections popping up out of a puddle, popsicle man, in squares or semicircles or triangles? No. It's starting off with revolving. Some calculus books start with cross sections and then go to discs washers. Some people do it backwards. I do cross sections first because cross sections, that forever card, didn't it give us basically the foundation to how to find volume in general, right? Because it said, in general, to find volume, all we need is area of the base times the depth, or area of the base times the depth in terms of x or in terms of y. We talked about the whole three-dimensional and how the integral will make them infinitesimally thin and make it perfect and accumulate it. I like starting with the slices because it gives you an idea so that when we go to discs and washers, it's like, oh, the pi r squared makes sense. The pi r squared is throwing in an area formula of the cross section. So that's why I start with cross sections and then I go to discs and washers. But anyway, I wanted you guys to see, oh, homework does it the other direction. Kiddos, each of these is going to be super similar to what we had today, except if you guys notice, oh, well, that's awfully nice. I was going to say all of these are in terms of what? And what are all of those in terms of, guys? X or Y? The way they're written. Uh-oh. In terms of? Y is gotten by itself, but they're in terms of functions of x's, right? So what do we really want all of the integrals to be? Dx or dy? Oh, yeah, but in order for that to be true, we need horizontal axes. What did I notice in every single problem? Oh, they're giving you horizontal axes. Well, that's nice. So all of these, 1 through 6, are going to be dx. All you have to figure out is, are they discs or are they washers? Just looking at it quick, guys, which of these are discs? If all of these are going around the x-axis, they're like starting you off super basic. Is that one a dx? Is that one a disc? Yeah, because it's flush. Is that one a disc? Is that one a disc? Is that one a disc? Oh, this is lame. They're all discs. Nope. Now, careful. They're showing you this little in-between, and that's good and all, but how does the washer formula actually work? Do you just subtract top minus bottom, throw it in a squared? Nope. We haven't gotten to see one yet today, but we will in that FRQ. How does a washer work? You need the whole thing minus the hollow thing, right? You need the big R minus the little r, or the top minus bottom of the big minus the top minus bottom of the hollow, right? As soon as it's not flush, we have to think of washers. Anyway, quick warnings as far as numbers 5 and 6. What's changing in 7 through 10? We're still setting up. We're still finding. But now, what do you guys notice about your revolution? And, oh, but the functions are still in terms of, so what are you going to have to do if it's dy and you have them in terms of x? Does this tell you what to do dx, dy? No. What tells you what to do dx, dy? The rotation, either what kind of axis, horizontal, vertical, or if you look at the little baby rotation arrow, the depth that it has, vertical or horizontal. Okay, what's going on over here in finding the volume? Oh, pictures are gone. So what do you, ooh. Has anybody gotten up to any of these ones, 13 through 16? What gets a little nasty? They say, hey, 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 you're revolving around him this time, him that time, him this time, him that time. Guys, let's do one of these in our notes. Which one do you guys have for homework? 13, because it's pink and it has a video? Perfect. I wanted to do 14 anyway. All right, number 14. Read the directions, because I'm not going to take a copy of that. The directions say, find the volumes of the solids generated by revolving the region bounded by the graphs of the equations and the given lines. So how many different solids am I dealing with? 4. I'm dealing with 4 different ones. I want you guys to go ahead and quickly get a sketch of y equals 2x squared with y equals 0 and x equals 2. And get me a quick little shaded region. You guys know what I mean, right? A quick little shaded region like you saw in the beginning of homework they were doing over here. You don't have to do the representative rectangle unless you want to. I just do a quick little line, a little slice, but either way. Let's see. How'd you guys graph it? What do you got? The function has a point at 0, 0, right? What else? If we plug in 2, we get 4. And then what was in between both of those, just to get some context? 2, and what are we doing? Swoop, there it is, approximately. And we could keep on drawing it, but technically, what region are they actually talking about, guys? If they say bounded by y equals 2x squared, y equals 0, and x equals 2. Oh, because I can't multiply? That makes sense why my parabola was funny. You know what's sad? I just didn't make my axis big enough. Because it's 2 times 4. Thanks, bud. Let me steal all those tick marks. We'll get some more. There we go. But guys, what region are they talking about? Are they talking about the region over to the y-axis, down to the x-axis, or somehow otherwise bound? What would you guys say? Where am I going to do my shading? Over to the y, down to the x, or some other variation? Down to the x. Why? Patricia, why did you say that? And what was the other part? Not just x equals 2. Yeah. So if you guys are looking at all of this, you have to be careful and you have to make sure everything is bounded. So x equals 2 needs to be a boundary of the region, right? Y equals 0 needs to be a boundary of the region, right? So I have y equals 0 here. I have x equals 2 here. And then I had my, of course, function y equals 2x squared over there. You guys see it? Okay, now where is it being revolved? Well, it's being revolved 4 different ways, true? So I'm going to go ahead and do this just because I'm cool like this, and so is my smartboard, except it just got all messy. There we go. So we're going to technically use this 4 different times. Oh, now they're all too big. How am I supposed to be revolving him first, guys? Okay, so I want you guys to put a revolution arrow, just like we did last year in pre-cal. You guys are tracking, right? The paraboloids, hyperboloids. That's going to be the end of chapter, whatever honors is starting right now, the end of chapter 10. Put your revolution arrow. Maybe some of you that like to draw, maybe you start sketching out what it actually looks like. Maybe the rest of you are like, forget it, I don't need to know what it looks like, I just need to know how to analyze it. Okay, we have 4 different ways of using this region, 4 different ways of rotating it. The first way, y-axis. Is it a dx or a dy? Because if you give it depth, well, you can either think it's a vertical axis you're going around, or if you give it depth, it's going to be a dy. True? Is it flush, or will it have some hollow? Hollow. So disk or washer. So somehow I'm going to have to go ahead and do v equals pi times a y1, or of an integral from y1 to y2 of some sort of big R of y squared minus little r of y squared all. We'll get back to plugging in just a second. But do you guys see at least why it's a dy and why it's a washer? Cool. Let's go look at the next one. We're just taking them one piece at a time. This guy, where are you going around? X-axis, so dx or dy? Dx, either memorizing a horizontal axis or looking at the little depth of what your rotation would be, which is horizontal. Okay, flush or hollow? Disk or washer? Take your axis, follow it as it hits the region. Is it flush against? Yeah, it's perfect. There's no empty space. This one, tons of empty space, right? This one, no, it's good. So therefore, disk or washer? Good. So I'm going to have pi, an x bound to an x bound of basically just r of x squared. Second. Somehow using right minus left, somehow using top minus bottom. Okay, next one. Where are we going around? Is that horizontal or vertical? It might help for some of you guys to visualize. This is an x equals 0, 0. Y equals was horizontal, x equals is vertical, right? Or just think y equals 8. Don't I go up 8 on the y-axis, and what do I do with that? I extend it. So guess where my revolution arrow is now? Here. Dx or dy? Dx. Either knowing that's a horizontal line or looking at it and visualizing your rotation arrow and saying that's a horizontal. But here's my question, guys. As you follow that axis and get to the region, is it flush against? No, look at all that hollow. So what am I going to have? Washer. So I'm going to have v equals pi. Still with x's, still with x bounds. So probably the same x bounds, I would think, as that one, but we'll check in a second. But I'm going to have my big R of x squared minus my little r of x squared dx. All right, una más. How about this guy? Where is he going around? What kind of line is that? Okay, so don't I go x-axis and I go over 2? Oh, wait. Don't I already have that line drawn? That's interesting. So I'm going around that guy? Okay, dx or dy? Do you guys see how I'm not drawing like amazing pictures? I'm not getting Joyce up here, well, she's gone anyway, to like show me all the shading and show me all the cool and how this is like really a big cylinder with like a cup hollowed out. I'm not doing that. I'm just, all right, dy. Or memorizing my forever card, it's a vertical axis. Cool. Follow your axis. Flush against, or is there hollow? Oh, so disk or washer. Nice. So v equals, oh, but it's a dy, so I'm going to have pi y bounds. Oh, hey, I bet they're going to be the exact same y bounds as that one with just a simple old r of y squared dy. Now, I haven't finished, but the basic idea, how are we doing? Following the axis, figuring out flush or not, whether it's a disk or a washer. Ooh, I should put parentheses, lo siento. They could have gotten me on that. Everything else should be fine. Figuring out if it's a dx or a dy, either visually or using the forever card and like memorizing it. But now it gets interesting, because now we have to actually plug in stuff. Now, guys, I don't think we need to see this anymore, so I'm going to go ahead and just extend the page so all I'm seeing are the pictures and my integrals. Okay, we need to be able to see the region and the axis for each one. Ready? All I'm going to do right now, and I'll have you do with me, is figure out my radiuses. If I have big R's and little r's, I'm going to have two different ones. If I have little r's, just one. Let's start with the little r's. Discs are easier. Okay, so I'm going, do you remember my clue from yesterday? Let me get a pen out. It'll make it a little bit easier. My hint was, yes, you can do top, bottom, right, left, but as you guys notice, things got really iffy there a second ago with these two guys. So my hint, out. If possible, go up. If necessary, go down, but go out. So I'm going to start at this axis right here. And I'm going to say, am I going right, left, top, or bottom to get to my region? Top. Perfect. That was the bottom. This is the top. Got him. That's my R. You see it? Just a representative slice. I could have drawn that anywhere. But if I drew that anywhere within the region still, who would be on top? And who would be on bottom? You see it? So when I go to plug into my integral, I'm just going to go ahead and say, okay, no big deal. That's going to be pi times, ooh, what are my x bounds? Oh, that's easy. What's the left x? What's the right x? Got him, coach. I'm going to go ahead and just throw in, what function is on top? 2x squared. What function is on bottom? Why am I having you write that? Because in just a second, it's not going to be 0 anymore. Okay. But then we can go ahead and rewrite that and say that'd be pi from 0 to 2 of 4x to the 4th. Are you guys okay if we just stop with the integral expression? What would you do in homework? If it's every third problem, you just throw it in your calculator. If it's not every third problem, you're solving it by hand up until 35. Was that it? The pink one, the graphing calculator. Let's go find, oh my goodness. Let's go find the other disk one. Okay. What was my hint a second ago? How do we draw our radii? Start from the axis of rotation, just in general. Start from the axis of rotation. Now, guys, look up here. Am I going from this axis? Am I going right, left, up, or down to get my radius? Left. Do you see it? I have to cover the region. So here, I was going from the axis up to get through my region. Here, I'm going to have to follow it, go left. Is that nasty? I don't know, maybe. But is it really? Once we follow the axis and then go through our region to the outermost edge, can't I just say the right? Well, who is the right? Good. Who's the left? Wait. It needs to be in terms of, all right. So we're going to have to go ahead and say x is equal to plus or minus the square root of y over 2. Okay, we have to choose one. Which one? Is it the positive or the negative? Wouldn't this parabola keep going? Do I want the side of the positive x's or do I want the side of the negative x's? The distance will be very different. Positive x's. So who's on the right? Sorry, who's on the left? What function am I using? The positive square root of y over 2. You see it? I don't want the negative one. He's way too far away. That would cover all of that region. No. I want this guy, the positive, or the right-hand side. Okay, so if I go to plug in, isn't it as easy as, oh, wait, we need y bounds. Okay, so how low does it go? 0. How high does it go? Use what Ryan said, not what I did at first. 8, right? So 0 to 8. And then who's being squared? Right, 2, minus left, square root of y over 2. Can I just discount this the same way I discounted 0 a second ago? No way, Jose, right? I can't discount him. Oh, guys, how would you actually solve this if you needed to? FOIL. No, but not, yeah. You would have 2 times the square root, a negative, that's 2 times the negative square root. You have 2 of those, so you'd have 4 times the square root. It'd be a little messy, but you could pull the root 2 out to the side and have the root y to the 1/2. You could do a power rule. That squared is going to be easy to integrate. This squared is going to be easy to integrate. The outer inner is going to be a little bit messy, but you can take away any coefficients to the front of that little piece and just think about your y to the 1/2. Anyway, but yeah, you'd have to FOIL and then go by hand. But we're just setting up the integrals, right? Okay, why did I do the disks first? Because they're easier. That's okay. Use what we just did and apply it. The whole minus hollow. Big R minus little r. Let's start with this guy. Yeah, let's start with this guy. Okay. What was my hint? Because I'm doing yellow every single time, either for the only radius of disks or for the big radius of washers. I'm doing yellow every time. That's where you should start. What was my hint for drawing your radius for both of these? Start on the axis of revolution and do what? Go through the region somehow to the outer boundary. Okay? So, start here. Where am I going to go through the region? Left, top, bottom, or right? So follow. Out. Guess who big R is? That guy. Out. Through the area to the outermost region. Or the outermost boundary, I should say. Go out. That's big R. We can label him. Who else do we need, though? Little r. So guess what little r is? Super similar. We start once again with the axis. This is hard for me to show. But you go the exact same direction, just not as far. You go to the edge of the hollow. So follow the axis. Now I could do it right on top, but if you guys are doing only pencil, it gets really complicated, so I separate it so you can see them differently. In my colors, you would have seen it, but for you guys, maybe not. So I'll go up here, not because it's proper. It technically should be right in line. But edge of the hollow. Do you guys see it? Little r. Because if we were to revolve this thing and have like a cylinder, I did not show that far enough away, but that's okay. If we were to revolve this thing and have a cylinder, and then we were to revolve this part, no, sadly I don't have my shading if I'm just working with colors. But if we were to have some of it being solid and some of it being hollow, it's a little hard to show. But if you were to pull this out, guys, it's a washer like we saw yesterday. This would all be solid, but then there would be hollow inside. And so the entire piece, the entire metal piece, before anything was punched out for like a washer, the entire piece is our big R. But the little part that was punched out, that was subtracted away, is our little r. But either way, we don't need to have all that visualization. We can follow the tricks of, no big deal, big R, little r. So when we go to plug in, okay, hold on, we already figured out our y bounds. What are our y bounds? 0 and 8. Now I'm going to go ahead and move him down because washers just take more space to write. All right, my big R. Who's my big R? Right. Right minus left, right? Big R right is 2. Big R left. Oh, I need it in terms of y. Good, good, good. So if I need it in terms of y, x is equal to plus or minus square root of y over 2. Why is Patricia telling me to use the positive? Because I'm not using the negative one. Someone help Michael out. He's struggling. So I have the square root of y over 2. There's my right. There's my, no, that's not my left. Look at the yellow. It's not like a disc. I can't just use my 2 curves. Look at the yellow. Right is 2, left is 0. Well, yeah, look at them. Right is 2, left is 0. 4 is the, well, not 4, sorry. 2 is my overall radius if it was just the cylinder. No big deal. But it's not just the cylinder. Minus. Now, what's the right of the little r? Good. That's my square root of y over 2. And what's my left of my little r? 0. You see the difference between disc and washer? Disc is like, subtract the 2 curves. We're good. Washer is like, no, 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 no. You have to subtract. And when you have to subtract, there's going to be one curve probably, or one equation probably involved in one of the r's and the other one involved in the other r's, and both of them need the axis to be considered as well. Now, could I make this simpler? Could I make this easier? Yeah, I suppose. So we'd have 0 to 8. We'd have 4 minus. And this one's going to look super weird because when you square him, it ends up just being y over 2. So they could have rewritten this a few different ways. You don't even really see any squareds in this, which is super awkward and super abnormal. Abnormal. But there we go. Okay, I'm going to make this a little bit smaller because we have one more washer problem to do. Okay. I want you guys to take a second. Think about this graph and try to figure out, just draw for me, who's big R, who's little r. Think about what we just did, what we did in the disks, how we applied that to the big R, and then we also did a little r. Who would big R be and who would little r be? Even just the picture. You don't even have to get it in equations. I want you guys to struggle just a little bit. But use my clues. Use my clues. As you're thinking about it, where are you starting from in drawing your radius? Good. AJ was saying it a lot, Janelle. Good. The axis of revolution. Where are you going? Right, left, top, or bottom? You're going down, right? So, go to the axis and go down. All the way to the outer edge. My finger's just being annoying. That's big R. Who's little r? Where do I start from? Same thing. Start from the axis and go where? Did you get it right? And if you were able to get it right, if you just carefully remember, you have to do top minus bottom. That was right, left, but you have to do top minus bottom when in terms of x. Were you guys able to figure out? X bounds are pretty much the same for the region. So V is equal to pi times 0 to 2. Big R. Someone's there, not mine, too short. Big R. Top is, who is that guy? Is that 8? 8 minus, isn't the bottom just 0? What's the top of the big, or little r? Still 8 minus, who's the bottom? Professional. Nicely done. So then how do we simplify it? This one looks a little more normal because usually it just looks kind of like this when you're expressing and you can kind of see like the big and you can kind of see the little and they're both squared. That one was weird because the square root squared went away. But either way, excellently done. Right in time. What did we see? Are you going to come up against disks? Yep. You're going to come up against washers? Yep. You're going to come up against dx and dy? Yep. But are there strategies to tackle the problems? Got this. You got this. Finish up homework for tomorrow. The sample FRQ, no big deal. We'll start off with it tomorrow. Unless you're like, I'm bored. I already finished homework. Well, you go tackle that FRQ. Bye, guys. Good job, good job, good job.